Hello, good afternoon, everyone. I want to welcome you to my lecture today. Of course, the other time I said that, statistics is like a story, cause a story that goes on and on and on. Okay, so, today I'm actually going to be walking you through what I call the instrumental variable regression. Of course, before now, you've been introduced to different uh, types of regression model. Remember, I walk you through the linear regression model all the way to nonlinear regression model. And of course, I also walk you through the regression type analysis, where the nature of the random, the nature of the response variable is categorical. And I also walk you through, the regression type, where the response variable has a nature that is discrete and that is also a rate or proportion, and so on like that. But, today, basically presenting you a regression type, that we actually normally refer to if there's a kind of violation. Of course, we normally consider this type of regression in a situation where we are trying to intervene, to be able to address an issue. Okay, give me 1 second. I'm actually going to share my lecture slide. Okay, so I actually need someone to confirm if you are seeing my lecture slide. Okay, thank you so much. Thank you for confirming that. So, like I said, today I'm actually going to be focusing on instrumental variable, regression. And of course, if you look at the word instrumental, it means we're basically going to be making use of some instruments as a variable in regression analysis. Of course, we actually going to do that. Whenever there's an issue, of course, I'm actually going to discuss that issue with everyone now. Okay, so in the outline, I'm basically, just like every other statistical model, of course, every statistical model has assumptions, because as we know, a model is as good as assumption put into a model. You get what I mean? Okay, so you know, in the outline, I'm going to talk about OLS assumptions and when they are violated. I told you the other time, the essence of this topic is actually that, there's a problem. And of course, we now want to have what I call an intervention. Okay, then I'm going to introduce you to instrumental variable approach. We got different kind of approach. We could talk about one endogenous regressor and one instrument. Then we're also going to talk about the assumptions for that. Okay, under the assumption, we're going to talk about the instrument relevance and instrument exogeneity. Okay, because before I can choose an instrument, it has to be relevant. So we got a statistical approach, to be able to figure that out. And of course, we're also going to talk about the exogeneity of the instrument. Okay, so I'm going to tell you all what that means. So, consider a situation where we're going to have one, endogenous regressor, one instrument and one control variables. There's a difference between an instrument and control variable. I'm actually going to walk you through on all what that means. And of course, we could have situation where we got one endogenous regressor and we got more than one instrument that I'm actually going to call multiple instruments. And of course, we can also have situation where, we got multiple endogenous regressors and also multiple instruments. Okay, all what I just need from you is just to sit back, and you ask questions where necessary. Okay, so I'm actually going to go into the problem of endogeneity in econometrics. Okay, let me first say this. When you're talking about fitting OLS, okay, into relationship, of course, we know we got a lot of assumptions that need to be had, like assumptions of linearity, assumptions of constant variance, assumptions of normality or independence, So those assumptions are actually required, okay? Before we can actually feed OLS, before OLS is basically going to make sense. But in a situation whereby the an independent variable is correlated with the error time. Okay, one of the assumptions is that we don't expect relationship to occur between a variable that is observed and the one that is unobserved. The one that is unobserved is actually hidden in the error time. So we don't expect any relationship to occur between what I call independent variable that you also call the explanatory variable or the one you call predictor and the error time. And don't forget, like I said, the error time, is basically going to be any other variable that could influence the response variable that we also call the outcome variable, that we don't talk about. Maybe the reason why we don't talk about it is simply because we believe its effect will be negligible. Maybe we actually thought it's not that important, and that is why it's actually hidden in the error time. But in a situation whereby relationship now exists, between what we observe that we actually call independent variable and the unobserved that we actually call the error time. Of course, it's a problem that we call endogeneity in econometrics. Okay, so it's actually called endogeneity in econometrics, and of course, this problem it is a real problem because it could make our model to be misleading. Okay, and that was why I said, yeah, that heterogeneity can arise, okay, as a result of measurement error, auto-regression with autocorrelated errors, or simultaneity and omitted variable. Let me also tell you this, the other time, when I was discussing panel data, I think I mentioned the fact that, when the a particular variable, that is very, very important, relevant, is missing in a model, of course, that's going to induce, what we call omitted, variable bias into so we're going to call that omitted variable bias. Of course, that would make the slope, the slope that you actually estimate to be inconsistent. You get what I mean? And we don't want inconsistency. Okay, so that could occur. Okay, so now even a measurement error could also cause endogeneity. So I'm just trying to talk about different kind of stuff that could lead to heterogeneity. Okay, so in the next slide. Now, some of you may be wondering what is the difference between multicollinearity and endogeneity. The two of them are not the same. Okay, the two of them are not the same. We're talking about multicollinearity. We actually believe a relationship exists among the independent variables. Okay, when relationship exists among independent variables, that's basically going to be a problem. We got a way to investigate multicollinearity. But when we talk about endogeneity, we're not talking about relationship between the independent variable. Of course, the independent variables in the models are the observed one. Okay, but the endogeneity arises when relationship exists, okay, between the independent variable and an unobservable effect, that is hidden in the error time. So I wanted to take a look at what I just said right now. Okay, the differences between the two, whether multicollinearity or endogeneity, they are problem in econometrics, and of course, what I'm going to be focusing on today, is how do we actually fix the problem of endogeneity. Okay. And that is why, even though there could be other ways of fixing that, but the one we are discussing today is the use of instruments that we actually call instrumental regression, variable regression. Okay, so we know endogeneity is going to be a problem, and what endogeneity is basically going to cause, by the time if you disregard that and you actually estimate the slope parameter, that slope parameter will be inconsistent, and of course, we all know the properties of a good estimator. Okay, the unbiasedness is there, the efficiency and consistency. Of course, um, it is not only that it should be unbiased, we also value consistency. Okay, and of course, the consistency property is is actually very, very crucial in statistical analysis. Okay, so so if I have a problem of endogeneity now, situation where the independent variable is actually correlating with the unobserved, I mean the other time, the variable that you believe is not important, that you hide in error time, okay, that's going to cause endogeneity, right? Okay, when it causes endogeneity, so how can we actually, what is the best way to deal with that? The best way to deal with that is actually to use instrumental variable techniques. And, if you take a look at what I said here, I actually said instrumental variable techniques, so which means there are more than one. Okay, so, but the one I'm going to be focusing on today, so what we call two-stage least square. Okay, two-stage least square. Okay, so that is the one I'm going to be focusing on. Okay, don't forget, what we're trying to achieve here is how we can actually fix the problem of endogeneity. I told you we're actually going to use instrumental variable techniques, but one of those techniques that I basically want to discuss is the two-stage least square. Okay, so the two-stage least squared, and of course we denoted that can be abbreviated as TSLS. Okay, take note of that. Okay, so I want to walk you through an example right now. Okay, for instance, I basically trying to look at the effect of the years of education on the wages. Okay, I'm going to say that again. Okay, you remember when I was walking you through the panel data the other time. Okay, I also use that example of, I use that example, right? Except that, in panel data, actually, we collected data across cross-sectional unit and over time. But here, there's nothing like that. Okay. Now, the the example of an instrumental variable, like I said, is a situation where we have wages and education now. They jointly depend on ability. You remember even I gave this example of ability, I think I gave ability, intelligence, those are the two, we have different kind of variables that may also influence wages that we don't actually capture in our model that we believe that we hide in the error time. Okay, what if in a situation whereby wages, which is the outcome variable and the years of education, jointly depend on ability. Right now, the ability is unobserved. The ability is actually eating in a narrow time. Okay, so I just wanted to take notes, okay, of that. Okay, now I want to talk about the purpose of instrumental variable. Okay, like I said, it's an intervention. Okay, that's a problem, right? Problem of endogeneity. And we're trying to see how that problem can actually be addressed. And of course, the consequence, right, of endogeneity, the slope, okay, that will tell, okay, how significant, is a contribution of years of education on experience cannot be trusted because it's going to be inconsistent, right? Okay. Now, so the instrumental variables are actually used, to control or for confounding and measurement error in observational studies. Of course, before now, we got two type of studies. You have the observational studies, you got the experimental studies, and of course, the experimental studies actually have a very strong statistical power, compared to observational studies, because of the way the participant are randomly assigned, to group. When you conduct experimental study, it actually give the participant, I mean, the researchers have a way to manipulate, you get what I mean, the participant. And of course, we don't have that opportunity when it comes to observational studies. And because of that, the observational studies is likely going to suffer what I call confounding. You don't have a confounding issue. You get what I mean? And how do we now control for confounding? Okay, in one of my video that I call a third variable, you remember when I was trying to talk about the fact that causation, correlation does not imply causation. You remember I said something like that. One of the reasons why correlation is not causation is because of the third variable problem. Okay, so right here, with the instrumental variable can actually be used to control for confounding and measurement error in observational study. And what with that, it actually allow us to have a possibility of making causal inferences with observational data, because they are very easy to make causal inferences with experimental data because the principle of randomization was actually used by researcher. I told you the other time they got a way to manipulate the participant, but in the observational study is not. And that's why the observational, in observational study, what you do, you conduct a survey or you use historical data. And of course, that does not have a very strong statistical power, but particularly when you are pursuing a causal goal. And of course, if you want to induce the idea of a causal goal, then it means we basically need to have what I call instrumental variable technique that we control for confounding, because the moment you are able to control for confounding in observational study, of course, you've already paved the way for causal inference. Okay, so let me tell you this. If I want to actually have an intervention right now, which is the use of instrumental variable, of course, there could be so many instrumental variables around, but, we basically need to be able to know the one that will work. Okay, the one that will work, the one that will fix the problem is the one that must satisfy a particular, condition. Oh my God, assumptions within assumptions. There's a problem initially, right? And the problem is the problem is called endogeneity, right? Situation where relationship exists between a variable that is observed and the one that is not observed. Okay, and we said, okay, because of that, when you go ahead and fit the OLS, you're basically going to mislead because the slope is not going to be consistent anymore. And, because of that, we are trying to, use instrumental variable technique to control the situation. And of course, well, how do I know, a particular instrumental variable that's basically going to work? Okay, how I know is the instrumental variable must also satisfy conditions, which I'm actually going to give now in terms of assumptions. We actually have a way, or to investigate whether a particular choosing instrumental variable we follow the assumption. So number one, a valid instrument must actually meet both relevance and exogeneity conditions. Don't forget, the problem was endogeneity, right? And we're not saying that the instruments must actually meet the condition of relevance and exogeneity conditions. So what do I mean by that? The relevance is actually trying to say, okay, you know what, it has a connection, okay, with the experimental variable of interest. Right now I'm looking at the effect of the effect of years of education, okay, on the wages. The instrumental variable I'm actually going to choose should be the one that is correlated, okay, that have a relationship with the years of education. Okay, that was why I said, the relevance. Okay, don't forget the other time, that a particular variable was hidden in the error time, and we said it's correlating with the observer explanatory variable, and that was what led to the issue of endogeneity in the first place. And right now, we want to bring something out of the error time now. Okay, and what we're bringing out, okay, as an instrument, okay, that particular guy now must be correlating with the explanatory variable of interest. Okay, that's what we mean by relevance. Relevance here means there's a connection, there's a linkage, there's a relationship, there's a correlation between the explanatory variable that we also call independent variable of predator. Okay, they have a relationship. Okay, now the exogeneity condition now, okay, is that instrument that we're choosing must not correlate with the error time. That instrument, of course, if it is correlating with the error time, then we run into another problem. In fact, that was even the problem in the first place. Okay, what actually led us, trying to figure out, trying to where we're making an attempt to try it out, the instrumental variable, okay, is just like, oh, there's a particular variable correlating with observable explanatory variable in our model that we hide in the error time. And you know what? We don't want a situation whereby the instrumental variable that we're going to choose is also going to be correlating with another variable that is unobserved. That's what we mean by exogeneity. Okay, so I want to take you into the model now. Of course, I know you've all come across, give me 1 second. I want to take water. Give me 1 second. Okay, thank you for that. You've come across, this particular model before. Of course, this is a simple linear regression model. Of course, right now, we statisticians, actually start with the specification of a model. Okay, take a look at what I have now. Okay, and of course, we got several assumptions for using OLS, the assumptions, take a look at this guy, or we're trying to say the expected value of UI. Okay, the UI here is an error time. Okay, given xi must be equal to 0. So what this guy is trying to say is that there shouldn't be any relationship between what is observed and what is not observed. You get what I mean? When I say what is not observed, I'm talking about the error time. What is observed, I'm talking about explanatory variable. Okay, that's what I expect. And of course, this is the second one. And of course, big outliers and stuff like that. Those are the assumptions. Okay. Now, those are the assumptions that we actually have for the OLS. Okay, so, and of course, I think I'm going to quickly move, now. Oh, give me 1 second. Okay, so now you see that for OLS, okay, you see the assumptions. Now let's talk about the instrumental variable now. Okay, we got this simple linear regression model. Okay, now what is the only condition under which we can actually use OLS? Okay, because if we can use OLS, we basically want to estimate the parameter of beta naught and beta 1. Okay, so what is of important to me now is a beta 1, which is going to be the slope, right? The one they call marginal in economics. Okay, so we actually want to obtain the consistent estimate of causa effects. Okay, and that can only happen if The outcome variable y only is depending on x, okay, the explanatory variable and the error time. When you take a look at this scenario now, there's no relationship between x and u, which means there's no relationship between what is observed and what is not observed. Okay, so I think I just demonstrate to you now, okay, where the condition under which the OLS can be used. But if you take a look at this condition now, even though y depend on s, y depend on u, but you can see here, there's a connection between s and u. Fitting OLS here, you're actually going to mislead. That's not good at all. Okay, so in this situation now, OLS cannot be used. And not only that, I'm going to discuss this second situation now. Take a look at this guy. Even though relationship does not exist between X and U, relationship does not exist between what is observed and what is not observed. But you can see here, the relationship should not be, uh, should not be what I'm actually going to call back and front. Like we don't want we only want a unique a one directional relationship. It shouldn't be a bidimensional, bidirectional. Okay, I say bidirectional. The bidirectional, oh, y depend on x also depend on y. In a situation where x also depend on y, then x is not truly independent variable. Okay, so under these two conditions, we cannot use OLS. Okay, I just wanted to take note of that. Okay, now the next now in a situation where what I showed you the other time, or whether days, okay, well, let me just say situation where this happened, right? Situation where this guy happened, this particular guy here, where the what is observed, in terms of independent variables depending on what is not observed. That I call the error time that led to the problem of endogeneity. Of course, what is going to happen is we can, by way of intervention now, okay, want to use, one endogenous, to use instrumental variable now. With the instrumental variable, we can use, okay, can one endogenous regressor and one instrument solve the problem? Now I'm going to walk you through all of that now. Okay, you got this as a linear regression model. Okay, now if this guy is a linear regression model, okay, and of course, we got this problem, this is a problem, right? Because that's a violation of OLS. Situation where the expected value of unobserved given observed is not equal to 0. You're trying to tell me there's a connection between them. That's a problem. Okay. Now, what are we going to do? We can't use OLS, right? So what we're basically going to do when there's this problem, we're basically going to use an instrumental variable Z. Okay. Now, if this is the idea, I'm going to walk you through the idea right now. Okay, I'm going to walk you through the idea now. Okay, you basically need to split your xi into two parts. This is the belief. This is the belief. The explanatory variable that I'm actually going to call observed variable, right? Okay, we actually believe that, it can be split into two. The very first one, the two part, the first part is going to be the one that is correlated with the error time, which is this guy. Okay, the part that is correlated with the error time. And the second part, the one that is not correlated with the error time. So that's what is our interest? Our interest is, okay, if I'm able to split the observed into two parts, okay, one part, okay, the one that is where that is correlated with the error time, and the second part, the one where it is not correlated with the error time, what we're looking for. We're actually interested in isolating the one where the variation in xi that is uncorrelated. I'm going to say that again. After splitting that into two parts, the first part is a correlated one, and the second part is the uncorrelated one. We actually want to isolate the variation in the uncorrelated one. Okay, so that we can actually use it. The one we grab now, the one we extract, that is uncorrelated one, okay, that is the one that can actually be used to obtain a consistent estimate of the causal effect of X on Y high. You remember the other time, I'm looking at the effect of years of education on wages, and we believe that the years of education may be correlating with unobserved effects like ability, intelligence, and so on like that. There could be other, uh, potential, variables that may be correlating on. Okay. Now, what we're trying to say now is, okay, the years of education now can actually be broken using method of instrumental variable, can actually be broken into two parts. Okay, into two parts. The first part is where, you know, uh, there's a correlation between the years of education and other unobserved effect. And in the second part is the one that will shows that, okay, they are uncorrelated. And you know what we basically need is to extract the variation in the uncorrelated, because the variation in the uncorrelated is the one that can actually guarantee, the consistent estimate of the beta one that we're actually seeking. You get what I mean? Okay, the beta one is the one that is basically going to tell us, on average, what is a statistical contribution of the years of education on the wages. Okay, I just wanted to take note of that, how it works. Okay, now, and I said here, in order to isolate the variation in SI that is uncorrelated with UI, of course, we're basically going to use instrumental variable ZI. Okay, we're going to use instrumental variable ZI. And I said something the other time. How do I know that the instrumental variable is basically going to work? Okay, it must satisfy two conditions. I talk about relevance, I talk about exogeneity. And of course, the relevance is more or less like, okay, you know what? The instrumental variable that I'm actually using is correlated with the observed explanatory variable. Okay, it's correlated with that. And that's why you basically have the fact that the covariance of ZI and SI not equal to 0. And not only that, it will also obey the exogeneity condition, which means the instrumental variable Z should be uncorrelated with the error time. Don't forget, the observed explanatory variable was correlating with the error time in the first place. That was why we're actually looking for a way out, okay, by actually considering instrumental variable. So the instrument that we're actually using should not fall into the same trap. That's exactly what I mean. Okay, so this is more kind of a graphical illustration of, all of that. Okay, now, as I'm still walking you through an example of, one endogenous regressor. When I say one endogenous regressor, of course, the regressor that I have working on was X, the explanatory variable. Okay, and one instrument, the instrument is Z. Okay, so take a look at what I have now. Initially, this is a linear regression model. Okay, if there is no problem of endogeneity, I'm actually going to fit OLS. But right now, what I'm going to do? I'm actually going to go, I'm for force work on this. Take a look at this guy now. Okay, the instrumental variable is actually Z. So I'm actually going to consider a separate regression where the explanatory variable is actually going to be acting like a dependent now on the instrumental variable. Of course, the essence of this is just to investigate whether there's a connection between the independent variable and the instrumental variable. Don't forget, under the assumption of the instrument, okay, there's something that we call relevance. And the relevance assumption is more or less like, is there a connection? Is there a linkage? Is there a relationship between the instrument that we're using and the independent variable? And that is the essence of this. So we're basically going to go by two steps, okay, because two steps are involved. And that is why it's going to be called or two-stage least square. We're still going to use OLS, okay? We're still going to use OLS, except that, we're using a special kind of OLS, okay, right now, okay? We would, of course, use OLX on this guy. And after using OLX on this particular guy, okay, then we actually going to use a certain information here to moving forward. Okay, this is what I'm going to do. We're going to go into first step now. In a first step that I'm going to call first stage, okay, using this particular model now, okay, I'm actually regressing. I'm going to regress, xi on zi, which is what this particular model implies. Then, what I need from this model, I basically need the predicted values, okay, of this guy. When I run this model, right, I can get the predicted values, right? I don't want to use, I'm not going to, in the second stage, I'm not going to use the original values of X, but I need predicted values of X. The predicted values that was actually obtained, putting into consideration the instrumental variable. Okay, now that's going to be first stage. And you know what, from here now, from here, of course, just like the way we always conduct a significant test when we evaluated the model, where we want to subject the model to diagnostic testing now, we can actually, we need to ensure that, the correlation does not exist, between the Z and the error time. Of course, the error time in this model now, okay, there shouldn't be any relationship. So which means this guy contain variation in X that is uncorrelated. Okay, so the variation in S, don't forget the other time I said, the variation in S that is uncorrelated with the error time is what I need. Now, in the second stage, in the essence of the fourth stage is actually to generate new set of values for independent variable. That's basically going to be predicted values now, not the original values. Now, what I'm going to do now? Then I'm going to regress, my Y on the predicted values. Okay, I'm regressing Y on the predicted values of X. Okay, now when I do that, that's will actually lead us to obtaining a beta one that is actually going to be consistent. Now, if you take a look at this guy now, of course, that's going to be formula. Okay, so the difference between the B2 SLS and just the B1 here is more or less like what we plug in here. Okay, you can see what we plug in. That was the mean of the predicted. But in the case of the OLS, it's not going to be the mean of the predicted X. Basically going to be the original X. You get what I mean, right? So that's what we call, that's the second stage. And that is why, because the OLS conducted in two stages, and that is why we call it two-stage least squared. Okay, so I hope you really understand that guy now. Now I want to walk you through the an example. And this example is actually coming from Stata, statistical package called Stata. So here we're actually estimating the returns to education. Okay, the returns to education, more or less trying to look at the effect of years of education on wage. Okay, and the data is actually coming from NLS Young Men cohort collected in 1976, among others, wages and years of education for 3,010 men. So the data are provided by Professor David Card. And of course, he used the data in his article using geographical variation in college proximity to estimate the return to schooling. Okay, now using Stata. okay, a statistical package. Of course, we actually have this output. When you fit linear regression, let's assume that, okay, we basically want to fit, linear regression and see if there's no problem. Of course, we know there was a problem. Uh, there was a problem of endogeneity because we have a way to investigate that there's a problem. Okay, we are assuming here there's a problem, but we ignore that. We ignore the problem and we actually feed it linear regression. And another thing I wanted to take note here, we basically focusing on the lane, the log of the weight, at times you can also we have a way, just to put the relationship in a very good statistical form. Okay, we can actually log one of the variable. Okay, so log of the wage is what we're regressing on the years of education. Now I needed to pay attention to this guy here, the education on this particular slope. Okay, when you take a look at this particular guy, the 5.57 whatever is a constant. Okay, the way and this guy is a slope. Okay, the way they are software or Python, they're going to report that is different from the way they start a package, going to return that. But let me tell you this, we don't expect the return to education to be likely to be consistent here. Okay, the reason why we can't trust this particular beta one, this is our beta one, right? We can't trust it. Okay, it's not going to be consistent. Or due to the fact that some important variables, okay, are actually missing. When important variables are missing, then that is going to make the observed one, which is the independent variable, to be correlating with whatever you put in there at time, which led to the problem of endogeneity. Okay, so we can't trust this. Okay, you can't trust this at all. Some of you, and that's why, when when some of you run statistical analysis, when you see significant, like if you take a look at this guy now, look at my p-value. The slope is statistically significant. Okay, this is not appropriate. You're using the wrong model. The fact that you are using the wrong model, okay, that makes it inappropriate. Does that make sense? So take a look at all of that. So D1 now is inconsistent. Okay. If the beta one is inconsistent, okay. So I just wanted to take note of that. Now, what are we actually gonna do? Okay, we need an instrument to be able to correlate that, right? Okay, so we want to be able to isolate, variations in the explanatory variable that is uncorrelated with the error time. Don't forget, the we actually well, we believe there's a problem of endogeneity situation where the years of education is actually correlating with the error time, and you know what we want to do now. The use of the instrument is just for us to be able to split that into two. Okay, we know we're actually going to have in a particular part, the years of education will be correlating with the error time. In another part, the years of education will not be correlated with the error time. That is exactly the variation we actually want to isolate. Okay, isolating that will actually be used to estimate, the slope that we can trust, the one that is basically going to be consistent. And that's why Professor Card in 1995 actually uses variation in college proximity. Okay, we can think of other instrumental, variable. We're talking about college proximity. How close is, your area to your college. Very, very important. You know what I mean, right? And that instrumental variable is looking, it's looking like a categorical one. Give me 1 second. It's looking like a categorical one. Okay, the proximity to college, you actually live very close to your college, or you live far away from your college. Okay, so which is we call one individual grew up in an area within a 4-year college. And of course, the individual grew up in an area without a college, without a 4-year college. What I'm trying to talk about here is that, okay, do I go up in an area? Okay, if you want to come, if you actually want to look at the effect of my years of education on the wages, okay, now what we're trying to say, the kind of instrumental variable you can think about is, do I particularly live very, do I grow up, in a particular area, with a 4-year college? Or without a college, without a 4-year college. Okay, so that is an instrument considered by Professor Card in 1995. Now, this guy now is basically going to act as our ZI, okay, the instrumental variable, okay, and the first stage of what you're going to do, if you remember what we did the other time, we're basically going to look at what is the relationship between the instrumental variable, okay, and education. Don't forget, in the model, that's the first stage, the education, the what was explanatory variable in another model, in a model that was problematic, is now becoming a dependent variable now, where you are looking at the effect of instrument variable on it. Because while you're doing that is to investigate the relevance between the two. You understand what I mean, right? And as you can see, that has been estimated. And of course, you take a look at the p-value, okay, or that turn out to be significant. All what we need here is just to also extract the predicted value of the years of education that we basically going to use in the second module. Okay, give me 1 second. So I just need to see all of that. Okay, so the step 2, we obtain the predicted values and perform the second stage. Okay, the predicted value of that was actually obtained, and what we did, we finally regress the log of wage on the predicted values of the years of education. The PR here means predicted value. Take a look at all of that. So this is a second stage now. Get what I mean? It's a second stage. Okay, now to quickly walk you through what happened behind the scene. Of course, all what we've been saying is actually how we do that using the starter package. Okay, so don't forget, if you want to use the two-stage least square, you first regress. Why? Of course, this guy, we got it from the first stage where we actually regress X on the instrumental variable. And of course, now we got a predicted value for that. Then we're now going to regress Y on this now. And of course, our beta cap for this 2-stage is basically going to see. So we're going to be look at this. Take a look at the what you see here. That's a predicted value, right? Okay. Now, if I really want to know, you know, what is going on, okay, I can actually do this guy now, okay. If we substitute, okay, uh if you take a look at initially what we have, okay, here I'm substituting the mean, okay, the mean of this guy from this guy, and the mean of this guy from this guy. Okay, that's what we're doing. Okay, that's the mean. So which model are we actually using? That is the first model, right? Okay, if you take a note, that is going to be the first model, right? Where we're going to have the S cap, okay, equal, okay, the pi cap not, okay, plus, the pi cap zi. Okay, so what are we doing right now? We're just substituting the mean of this from this, mean of that from that. That was what led us to that today. So when you simplify mathematically, you're actually going to arrive at this guy. When you simplify this guy here. So what you're going to see in the end, mathematically, you're basically going to see the intercept canceling out. Then you factorize for pi cap 1, then you're basically going to have this. Okay, so when you have that guy now, okay, when you have this guy now you actually gonna plug that in, okay, where you can see this guy, right? S minus S cap. The X minus S cap is here. is also here. Then I'm actually going to plug in this guy now. When I plug that in, that's what led to this guy, right? Okay, when I simplify mathematically, okay, I'm actually going to have this guy. Okay, when I have that guy now, the simplification, oh my God, take a look at what I have now. Okay, so now I'll have this guy and say, since this PyCap one is a first stage OLS estimator, okay, so I can basically have this multiplied by this, I'm just gonna, if you take a look at this guy now, okay, so that guy is basically this guy. So what I'm trying to tell you now, okay, is like the reciprocal of the pi cap one, okay, in the first module where I was relating the conventional independent variable with the instrumental variable. You understand what I mean? And the reciprocal of that is basically this guy here. And at the end, when you actually simplify that, this is going to lead us to what I call the instrumental variable estimator. Oh my God, this is an instrumental variable estimator now. So take a look at that. Okay, now, actually, do you know that what we did the other time that we go by two stage, like first stage, second stage? Okay, it would be more beneficial if you can just run it once. And that was why I said we can obtain the two-stage, 2SLS estimator in two steps as we have seen. But however, the standard error reported in the second stage regression are incorrect. Okay, in the second stage regression where you're going to actually regress Y on S cap, okay, Y on the predicted. The predicted X, the one you don't forget the predicted X, you get that from the first equation where you actually regress X on the instrumental variable, right? Okay, it is mathematically proven and statistically observed, that the standard error will be inaccurate. And in order for us, to solve that, to correct that, SATA did not recognize that it's a second stage, okay, of a two-stage process. So it fails to take into account your salary in the first stage estimation, and instead, we can actually use one step for two SLS. And how is it going to happen? Okay, how is going to happen in starter? Of course, this is basically going to be the code. The moment you have your data in, this is the code, to say IV regress, okay, to SLS, IV regress. I'm not trying to say, instrumental variable regress to SLS. Okay, don't forget, this is the response variable. I call the outcome variable. And what you have here is, I said, education equal to near college. You remember, okay, education equal to near college. The near college was actually the instrumental variable considered by Professor Carr, 1995. Okay, and in the end, we got this result now. Okay, this result can actually be trusted. Okay, this result can actually be trusted compared to the other one. Okay, so I think I'm actually going to stop here today. And of course, in the next lecture, I'm going to, walk you, through this further. You get what I mean? So, is there any question today? Okay, so I want to believe that you understand the idea of, the way instrumental variable regression work. In the summary of what I've done today, situation where there's a problem of endogeneity. And of course, what led to endogeneity is when there's a correlation between the observed independent variable and the unobserved. The unobserved is the one in the error time that actually led us to the problem of endogeneity. And of course, the way out is basically to consider method of instrumental variable techniques. And one of the method of instrumental variable techniques is what we call a two-stage least squared. And of course, the reason why you call that a two-stage least squared is basically you actually you need to first identify an instrumental variable in case you are using one instrument, and that particular instrument must pass two tests. Number one test is passing a test of relevance, and number two is it has to be pass a test of exogeneity. Okay, so well, we believe that the moment we choose the instrumental variable, we'll be able to isolate, the variation, in the independent variable that is uncorrelated, okay, with uh, with the error time. Don't forget, when I say correlation between the independent variable and the error time, which is unobserved. Of course, I gave you an example where we're looking at the effect of years of education on the wages. And of course, there's basically going to be a problem of violation of OLS assumption that actually, in this case, called endogeneity right now. And of course, we can't fit OLS, and we basically want to fix the problem using the one instrument. And of course, the instrument we actually choose according to Professor Carr in 1995. We actually consider the proximity to college. Okay, the proximity to college here is a categorical variable, is being used as an instrument, and of course, with that in the module, we'll be able to isolate, the variation in the years of education that is not correlated, okay, with the error time, because the variation in the independent variable that is not correlated with the error time will enable us to estimate what I call, consistent beta one, right? We call slope. Of course, if you ignore that threat and you go for OLS, of course, your beta one is basically going to mislead because it's going to be inconsistent. Okay, so I've walked you through all of that today, and of course, I'm basically going to continue from where I stopped. Okay, so make sure you all stay safe and have a lovely day. Bye for now, everyone.